And if it works well, then I think possibly we're going to switch to Hangout for the classes. Okay. So I think I've already lost some time, almost half an hour today. Okay. See, the what we've been doing last class is to actually look at BCNF, okay, Boy's card normal form. Given a relation, how we are going to make that relation into Boy's card normal form, and we are also trying to look at third normal form, and then I have to go on to second normal form and first normal form. Okay, that's where I am last class. To just recap, determines the value of B. Just to give an idea of what we gave was last time. Quick recap. Okay, so what we've done is we have actually looked at if something like the state capital, this kind of a thing exists, city, state, and capital, the information about state and capital gets repeated in this relationship called our city, state, and capital. Okay. So when this happens, when the state capital changes from Hyderabad to Amravati, we have to update it in multiple states. And there is a voice back from here. No? I'm getting a feedback on the voice back to me. So, this is what we are talking last time, okay? And then this is the golden rule of data. Okay. So this is what we were doing last time. And if you split this relationship into state capital and city and state, no data is going to be duplicated. This is what we were actually looking at last time. Okay. So typically the problems are you want to avoid duplication relating to that the update anomaly and also the deletion anomaly. These are the three things that we want to avoid in relations. So the golden rule of database design is one fact at one location. This is what we want to achieve. Okay. We also looked at the concept of keys and super keys. Okay. If there is a relation R, a set of attributes. Okay. And not any of its subsets. Okay. So then we call that as a key. We gave an example of a key. If city is named, becomes the key. If city names can be repeated but not in the same state, then city plus state becomes the key, right? This also we saw last time. We also saw the concept of super keys. Super keys contain the keys, all other attributes. But then, for example, here if the key for this relationship is A and B, then all the, for example, A is the key for the relation here, R, A, B, C, D. If A is a key in the relation R, then the super keys are formed with this key. Okay, so this will contain the key. All these will be super keys because they contain the key A in this particular case. Okay, these are all super keys. Okay, right. We also gave this one more example of a star, and if the star name is not going to be repeated, star becomes the key, and all supersets of star will be super key for the relation movie. This also we saw. We also saw the concept of what is a trivial dependency. If the right side of the dependency is a subset of the left side, it is trivial functional dependency, because as you can see here, we're starting with A and B. The values are in a tuple. If it takes a value, particular value for A, particular value for B, that tuple is going to, two tuples will agree on the value of A and B. They're suddenly going to agree on the value of B, because B is, they're already agreeing because of the left side on the value of B. So as far as the right side is concerned, they are going to agree because it's a subset of the left side. This is what we call by trivial dependency. Okay. For example, if you just take A determines B, then that's not a trivial dependency, functional dependency, because when two tuples agree on the value of A, they have to agree on the value of B. Here, when two tuples agree on the value of A and B, what we are saying is they also agree on the value of B. This is trivial because we have already B is included in the left side. We're saying that when they agree on the value of B, they'll already agree on the value of B. Okay. So this is also what we call as a trivial functional dependency. Okay. Last time we started off with this thing where Boyce Codd normal form. This is the highest normal form as functional dependencies are concerned, and we the left hand side of the functional dependency, the left side of every non-trivial functional dependency in the relation has to be the super key of the relation. Okay, this is the requirement for the relation to be in Boyce Codd normal form. Such a relation R will not have any duplication of the information. It will only store one fact at a time, and hence there's not going to be any duplication, and hence will not have any anomalies, update anomaly or deletion anomaly as far as that relation is concerned. And hence it is a good form. The relation is in a good form because it is not containing any duplicate values. Okay, that is the idea of BCNF. So when a relation has functional dependencies, we would like to actually see if the relation is in BCNF. It's said to be in BCNF only when the left side of the relationship satisfies this condition that it has to be a super key. For every functional dependency, the left side of the relation is a super key for the relation, then it actually satisfies the BCNF requirement. It is easy to understand when a BCNF requirement is satisfied, then there is absolutely not going to be any duplicates because we're saying the left side of the functional dependency is a key. Once we are saying the key will not get repeated because key uniquely identifies the tuple that guarantees that every functional dependency, the fact depicted by the functional dependency will never get repeated in the tuple in the relation because every tuple will be uniquely identified by that key, and hence the fact that x determining y will not get repeated because when a particular x, a particular y value will appear only once in that particular table. Okay, that is what it is ensuring by making the relationship to be in BCNF. Okay, this is what we're seeing last class. Okay, we're just seeing, for example, if you take this example, city, state, and capital, the first functional dependency, the city determines the state and the capital. Okay, and the functional dependency, two states, that state determines the capital. Okay, since we are assuming that city names are unique, okay, city becomes the key for the relationship. So FD1 satisfies the requirement, BCNF requirement, that the left side of this functional dependency is a super key, which consists of the key, which is also a key. A key also is a super key, right? It has the key. Okay. Whereas the FD2 does not satisfy BCNF requirements since state is not the super key to the relationship. If you take state here, given a state Andhra Pradesh, its capital is Amravati. Okay, this is what we are talking about. If you take this Tamil Nadu, then its capital is Chennai. So this FD2 requirement that in this relationship, the state determines the capital. The state is not key in this relationship, and hence the state and capital information is going to be is a key in this relationship. What this says is every tuple of this relation is uniquely identified by the value of the state, and hence state would not have repeated. Okay, so what BCNF is trying to do for you is, if there is a functional dependency, here the functional dependency is state and the capital. You can look at the table that we generated previously for this. Okay, right? This is the table. Okay, now you can see Vizag. This is the key, so this won't get repeated. The city is the key in this relationship, so you can ensure for all practical purposes purposes, the city information in this table will not get repeated. City will be uniquely identifying every tuple. Vizag, Kakinada, Hyderabad, Rajahmundry, Tirupati, all these, right? Chennai, all these will be unique. The city names are going to be unique. But if you look at the dependency state to the capital, this is what we are talking about. This is a functional dependency. But in this particular relationship, state is not the key. Okay? Since it is not the key, it gets repeated. As you can see here, this dependency, AP determines Hyderabad, AP determines Hyderabad got repeated because in this relationship, state is not the key to this relationship. Only city violates the BCNF requirement. If it satisfies the BCNF requirement, this will not get duplicated. This information that Andhra Pradesh as a capital, Hyderabad or Amaravati. For example, now you want to change it to Amaravati because of this reason, since there is duplication here, you have to change it at multiple places, 3 places. This is where the update anomaly comes. Okay. From this table, for example, if this only tuple that is there in Hyderabad, Telangana, Hyderabad, if this is deleted, the fact that Telangana has the capital Hyderabad is also lost because of this deletion of this tuple from this list. Okay, so that's the reason why if a relation violates the BCNF requirement, then duplication will occur. Okay, along with duplication, the update anomaly and deletion anomalies also occur if a relation is not satisfying the BCNF requirement. For example, the same thing will not happen if you have actually split this relationship into 2 separate relationships. For example, if you put this relationship, relation city and state, C is the key now here. Okay. Now you can see this is not going to be repeated. To which state it will belong, that will get given here. Similarly, state and its capital. Okay, now as you can see here, there is a state, Andhra Pradesh, and its capital is Hyderabad. And state is the key now. State will not get repeated twice. Every state will be key in this relationship, and it will be only once. In the tuple, every state will appear only once because it's the key. Okay. Now you can see Andhra Pradesh has Hyderabad, Telangana has Hyderabad, TN has Chennai, Kerala has Trivandrum. Now if you update, for example, AP's capital to Amravati, you just have to go to one place and then update. So both these relationships are in BCNF. Look at this functional dependency, city to state. Okay, this is the only FD that is available. The left side of the functional dependency, city is a key in this relationship, and hence this is in BCNF. So this will not suffer from any duplications. Look at this relationship, state to capital. Okay. Now this state to capital, there's a functional dependency. State determines the capital. Again, state is a key in this relationship. Okay, it will not get repeated, as you can see. The tuple will, every state will appear only once in this table, and hence this information also is not going to get duplicated. Okay, right? This is what we mean by the a relation being in BCNF. Okay, right? Where we say for every non-trivial FD of the relation R, the requirement is the left-hand side has to be the key. If the left-hand side is to be the key in the relationship, this the fact that this left-hand side determines the right-hand side for a given value will not get repeated in the table, and hence will not suffer from same duplicate data being present in the table. This is what we mean by the BCNF. Okay, I hope with this BCNF understanding is very clear. BCNF is the highest level of normal form that you can achieve when functional dependencies are present on the data. Okay, and once a relation is in BCNF, no duplicate, no duplicate data is going to be present in the relationship. Freely on the board, as I'm speaking, as I'm doing the lecture, I can do a few more examples on the board, and it becomes easy as with the use of the board. Okay. Okay. Now, one more example is this property record. We did this last time in the last time on the board. Okay. The property record, we have the property ID. This is a uniquely identifies the property. The city identifies the city in which the property is located. The house number indicates the house where the property is located. The area is area of the property, price, the price of the property, and tax is the tax associated with the property, okay. Now we can assume, if you assume that property ID uniquely identifies the property record and hence key to this relationship, which means that this relation, property ID uniquely identifies the tuple. It will not get repeated, okay. It will be present only once in the tuples in this record, property record, okay. Let us assume city and house number are also going to be unique. For any property, given property, the city and the house number can also be assumed to be unique, which means that they also identify, they will not get repeated, and hence you can see that this will not get repeated. This is also a candidate key. So there are two candidate keys for this relationship. One is the property ID, the other is the city and the house number, okay. This also uniquely, and there are two candidate keys. These are important. At a later point when we do the course, we're going to see that when there are two candidate keys, one of them will be designated as a primary key, and we'll use the primary key for indexing purposes, okay. We'll try to see how to index and search and then retrieve the information when we talk about indexing all these tables, okay. That's a separate subject by itself, okay. So the functional dependencies in this property record is the property number determines the city, house number, area, price, and tax, okay. All the other attributes are determined by the property number. Given a property number, all these will agree on, okay. There is not going to be two properties with the same number but not agree on the city, house number, area, price, and tax. That makes no sense because you're uniquely giving for every property a unique ID number called the property number. Similarly, city and house number together is what the property is identified. That's how the property number is given. That also uniquely determines, this functionally determines. City and house number also functionally determines the property number, area, price, and tax, okay. We can also put an FD3 additional functional dependency in this relationship that the attribute value tax is determined by the city. For example, we were saying this. City, one city, Hyderabad can have one tax, Amaravati, Vijayawada can have another tax. So given a city, the tax is determined, okay. It is common across all the cities, okay. Given a city, the value is fixed. For different cities, it is going to have different value, okay. Similarly, given an area, for example, 1,000 square feet of property, the price is fixed, okay, right? That's what FD4 is saying. So you can say that these are the four functional dependencies in the property record. All this is saying is there is an R. Previously, go to the example. In an abstract sense, R is a relation name. In this particular case, it becomes the property record, okay. This is equivalent to saying, I will sort of, for you to understand, since I'm not using the board, I will sort of give you this becomes the R, A1, A2, A3, okay, and A4. How many are there? A4, A5. There are 5 attributes, okay. A1 corresponds to R, property record, the relation name. This corresponds to R here. A1 corresponds to property ID. A3 corresponds to A3 corresponds to house number. A4 corresponds to area. A5 corresponds to price. A6 corresponds to tax. Okay. Now, if you want to, in an abstract sense, want to write these functional dependencies, all that you're going to say is here. Okay. A1 determines the A2, the values of A2. Given A1, it determines the value of A3, A4, A5, A6. Okay, like that you can write. Each one of them will. This is the first functional dependency. Okay, the second functional dependency is A6. Determines. Sorry, city and house number is also a key. So this determines now. I think we put the other ones there. Okay, in the later part. But then I'll write now. A2 and A3 together will determine A2. Sorry. A2, A3 functionally determine all other attributes. This is what we are going to write. Now A1, A4, A5, A6. Okay. We can also say for the other functional dependencies, city determines the tax. Okay. That is A2 functionally determines. Okay. Tax is A6. Okay, so this is the other functional dependency. Okay, now the final functional dependency is area determines the price. Okay, this is A4 determines A5. Okay, this is what the other functional dependency is. Okay, right. Now, what is the requirement? The left side has to be a key. Now you look at this A1 because of this functional dependency. A1 has to be key. Now you can see here. Property ID uniquely identifies the property record and hence key to this relationship. So A1 is the key. A1 is key here. Okay. Now you can see here because of this functional relationship, A2, A3 is the other key. Okay. A2 and A3 is also a key. Okay. So this also satisfies these two functional dependencies now. Satisfy the requirement for BCNF. They will not get repeated, okay, in the relationship. So there is not going to be any duplicate. Look at A2 and A4. Okay, A2 is not key in this relationship. It will get repeated for different house numbers in the same city. The city value is going to be repeated because city is repeated. Since city determines the tax value, which is A6, will also going to get repeated several times. This FD will cause duplication of data. Similarly, A4, price area determining the price in this functional dependency also causes repetition of the data in the table. So because of these two, this relation R is not in BCNF. Okay. Right. Okay. So this is what it is. I've just put it in the abstract sense. Okay. Is this in BCNF? No. Hence the relation is not in BCNF. F1 and F2 satisfy the BCNF requirement since LHS of both FDs are keys to the relation. Okay. FD3 and FD4 do not satisfy BCNF requirement since they are not keys. Hence the relation is not in BCNF. Okay. We will go more deeper into how to split the relationships, what more things you should be worried when splitting the relationships. But suddenly the ones which are causing the problem for you, you can sort of get them out of the relationship and then put them as separate relations to get the relations into BCNF. Okay. Now we need to split the relations into sub-relations. Okay. When you're splitting these relations into sub-relationship, we need to still worry whether these three together will represent the same original word or not, which means that a join on these three records, on these three relationships, has to produce the same original relationship. Okay, this should be a lossless decomposition. When you actually have this original property record information, now you break this into this three records, three relationships instead of the original relationship. All the original records should come back when you join all these three relationships. Okay, then only it is called lossless decomposition. That's what first thing we have to realize. The second thing is the dependency preservation. For example, these are all the FDs that are present in this. These are dependent on the attribute values. This attribute determines this. These two attributes determine all those other attributes. These are dependencies. The same set of dependencies should be preserved on the split relationships also. Okay, so you can't just arbitrarily split a relationship into some sub relationships. You need to worry about the dependency preservation and lossless decomposition. These are the two properties. Okay, first thing is it has to be lossless. You will also like to have dependency preservation. Okay, as far as this decomposition is concerned. But just to get the point now, since the property number, city, house number, city and house number are keys in this relay, they continue to be the keys. Area becomes functionally determined by this. Since that's the only functional dependency that is available here, and both left-hand sides are keys now for this relationship, this is in BCNF. Similarly, tax record, city determines the tax. City is the key to this relationship, and hence this is also in BCNF. Price record, where the area determines the price, also is in BCNF, because area now determines now determines price, which is the functional dependency, and area is the super key for this relationship. Okay, so by splitting the original relationship into three sub relationships, you got the property of BCNF to these relationships. Okay, I hope up to this point it is very clear. Okay, we need to still do a lot of homework. For example, as I said, the split has to be made lossless and should be dependency preserving. So we have to see when this thing becomes lossless decomposition and when the dependency preservation property will be will be obtained when this decomposition takes place. So we have to see some merits behind it. Okay, right now I want you to understand the intuitively what we are doing. If you understand something intuitively, you will never forget. Okay, that's the first requirement. So you should see why we are doing this, why we are doing BCNF. Okay, why it is a good thing to be doing for a relational model. First, you should understand that so that you'll never forget that. This is one of the most common interview question you will face everywhere. Okay, given a relation, now how do you determine whether it is in BCNF or not? Okay, right. So the requirement is the LHS of every functional dependency in the relationship has to be a super key on all non-trivial functional dependencies. Okay, right. More on functional more on functional dependencies and keys. Okay. No? The video are there any questions? Are there any questions? I'm getting a feedback. Hello? I don't know how effective it is. Okay, right? Hello? Can I continue? Yeah. Okay. So, okay. Yeah, because I'm not seeing the students. I'm actually, it's more like talking to myself. Sitting in my lab and then talking to the computer. This is a new form of teaching. So this will have its own. Yeah. No, it's okay. And see, what I'm saying is, it's only I'm actually, for me, I know, for me it's new, right? So I have to get used to this. Yeah. Okay, let me go ahead. I think I have some material to cover, and I think maybe I'll do some tutorial sessions for them. I'll start, having problems, and then I solve the problems for them on the board. Okay. That might make things. Hello. Yeah. That might make things more easier for them. getting a feedback doesn't really matter at this stage. So let me see how effectively we can communicate as much as possible. Okay, right. So if you're actually looking at functional dependencies, more on functional dependencies, because as I go further, I need to do a little bit on the closures. Okay, which I think I started doing in the last class, but I have not no fully finished the closure part of it. What is closure and how do we actually look at closures? Okay, I'm going to do. Hello. Yeah. Okay. Um, Hello. Yeah. Can I go ahead? Okay. Okay. So there are certain things that one needs to preserve as part of the relations. So in this particular relation, as you can see, there are actually three attributes, and these are the functional dependencies in this in this. Okay. In this relation dependency. Now, when you actually look at reflectivity property of the functional dependency, when B is a actually subset, I can't get the, so I'll just like B is a subset of A. Okay, this is trivial. Okay, it becomes trivial. Okay, and this is what is called no. Okay, this is called reflectivity property. Okay, the augmentation rule, this is actually called reflectivity. The second one is called the augmentation. This is called reflectivity. Okay, it is reflexive. Okay, the second one is called the augmentation rule. The augmentation rule, as you can see, given A and B depend on each other, you can actually add C trivially on both sides. Okay, they agree on A and B. Whenever a value of A is there for a tuple, they agree on the value of A, they agree on the value of B. Now, what you're saying is when they agree on the value of C, B and C, they also agree on the value of B and C. C being common, again, they trivially will agree. AC will trivially determine also BC. Okay, by adding this C, you're not changing anything. AC now determines BC. Okay, earlier A is determining B. Now you're saying instead of A determining B, which is correct. You're augmenting that now. AC determines BC. Okay, this is called the augmentation rule. The last one is the transitivity rule. As you can see, A determines B. Functionally, if A determines B, okay, this is what it is. A determines B. That means when in the relation R, whenever a tuple agrees on the value of A, we are saying that it also will agree on the value of B. Okay, and we are also saying because of this, when you look at the value of B, it also agrees on the value of C. Okay, this is the other functional dependency. This both together imply now A also will determine C, because for a particular value of A, the B value will be fixed. For that particular value of B, the C value will be fixed. So if you take A and C, A also fixes the value of C. So two tuples, if they agree on the value of A, will also agree on the value of C. Okay, these are called Armstrong's axioms. Okay, they are actually sound and they are complete. So given a set of functional dependencies, using these three axioms, you can derive more functional dependencies, and we can show that mathematically. I can go deep, but I'm not actually. I'm avoiding all of that, because this is also a remote class. I can only point out. I can give the reasonings. For example, you can take two tuples and easily can take the specific values and prove that these three rules apply for the functional dependencies. Okay, right? They're also called Armstrong axioms. Okay, and it is easy to show that these Armstrong axioms are sound and complete. Sound means whatever this axiom derives as a new functional dependency, that will hold. It will only derive functional dependencies that will hold. That's what we mean by sound. Complete means whatever is derived, no, nothing else more than this can be derived. So both these axioms are both sound, and all these three axioms are both sound as well as complete. Okay, right. So we are going to use them, for example, for actually first looking at closure of attributes, okay, and closure of functional dependencies. Okay, I think probably have the closure of attributes here. I'll just add one slide here. Okay, as you can see, I'm actually um, I'll just add after this Armstrong axioms. Okay, one slide on closure of functional dependencies. Okay, closure of FDs. For example, if you have A determines B as one of the one of the A determines B, and then B determines C. Okay, I'll give a couple of examples here to make you see what I'm trying to do. Okay, then we can say, let us say D determines A. Okay, these are the, let us say the functional dependencies on the relation, okay, or A, B, C, D. Okay, these are the functional dependencies. Okay, or okay. Now, what are the other functional dependencies that we can derive based on these things? Suddenly, from transitivity property, you can determine, okay, that this is the other functional dependency that you can get. Okay, given that the initial one is F, you can keep on now deriving new functional dependencies that apply. Okay, now D determines A, and then A determines B. So you also can derive through transitivity that D determines B. Okay, this is the other one. Okay, right. Now since B transitively determines C, then you can actually put D transitively determines C also. Okay. Now you can see I'm able to now derive more dependencies, more functional dependencies by applying those three rules, okay, three axioms, Armstrong axioms. I can actually derive more dependencies. Given an initial set F, okay, F of functional dependencies, F of FDs, if you are able to now apply all these axioms and get to what is called the full set of functional dependencies, that is what we mean by the set of functional dependencies that one can get, that is called F closure. Please understand, this has to be superscript. This is called closure of F. Okay. Given the set of initial functional dependencies, all the other functional dependencies that you are able to derive out of it is basically called the closure of the functional dependencies. Okay. For example, in this particular case, all the FDs given A, B, C, D attributes, and given the set of three functional dependencies, I'm able to derive more functional dependencies. A by transitivity property, A determines C, D determines B, D determines C. Like that, I can actually now, using the augmentation rule, I can further define more FDs. All the FDs that apply on this R, A, B, C, D, given the initial set of FDs, is basically called the closure of F. Okay, right? We are going to use this closure property later. Just understand it now. Okay, I'll use the closure properties for defining the lossless decomposition as well as dependency preservation. Whatever I'm doing now as a concepts. Okay, they further help me in defining those. Okay. Hello. Attributes. Okay. Now you can see this is, I think, something that I started doing and also told you how to actually determine the key for a given relationship. Okay. This is an interesting FD. I'm going to do some more problems using this. As you can see, there's a relation R, A, B, C, D, and the set of FDs that are defined on this R. This is an example that I'm doing. Okay. AB determines C, C determines D, D determines A. These are the set of FDs that I have on this relation A. Okay. Given an attribute closure, we previously look at the FD's closure. We can also look at the attribute closure of attribute set. For example, just take the A as the initial attribute set, and you want to now find out, given these FDs, all those attributes that are actually determined by this initial set. Okay. Now, for this, what do you do now? What are all the other things A can actually determine? Okay. Now, in this set, as you can see, if you start with A, which are the functional dependencies on the left side, which determine the right side. Okay. A alone is not determining any other attribute here. Okay. So we can't add any other attribute into this set here. So the closure of A, attribute set A itself. There is nothing else that can be added here. Okay. Now we start with AB. The initial set of attribute set is A and B. Okay. If you start this and want to compute the closure of this attribute set, apply the FDs now. Okay. The left hand side matches AB. You can see this FD1 matches. AB determines C. Now add C into this set. Now this set becomes ABC. Okay. Now C determines D. Okay. Now you can also add D into this set. Okay. Now we have come to the complete set of attributes. No more sets anyway can be added. Even if D determines A is already in this set. Now you can see this is a complete set that can be determined. Initial set is AB and the closure of this is ABCD, which is the full set of attributes in R. If this is the case, this AB becomes a key because AB now determines all the attributes of the relation. Okay, that's when we call AB as the key to this relationship. A is not a key in this relationship because functionally A doesn't determine any of the other attributes B, C, D. Okay. Now you can also see if you start with an initial set of BC, okay, and want to compute the closure of B and C. Okay, this is a bit tricky now. Okay, first you have to apply C. Okay, C will get you the D because the left side C determines the D. Since you have started with BC, D becomes part of this set. Now, when you add D, D determines A, so A also becomes part of this set. So when you actually compute the closure of BC, set the start set of BC, then BC also becomes a key. Okay, same thing BD. Now you can see, AB is a key to this relationship. BC is a key to this relationship. BD is a key. No subset of this is a key. For example, if you take B alone, the closure of B alone, like this, you can compute. Okay, B alone doesn't determine anything, so it will be just B itself. Okay, if you take C alone as a starting set, you can add D into it. Okay, but nothing else will get added. I guess D adds A, but then D will never get added by that. So if you start with C, you will get CDA as a closure set, but B you will not get, and hence that is also not key. If you start with D, you can add A into it, and nothing else can be added. So the closure for D attribute is just A itself. Okay, right? So to just finish there for you as an example, right? So if you want to compute the closure of B, okay, it's going to be only B itself. So it's again not a key. Okay. C is going to be the closure of, if you start with C, like this you have to compute. The starting of closure of C is going to be now, this is going to be, the closure is going to be, I'll just do this and stop there. Okay, C is already initially there, then D comes, then because of D, A comes. But B doesn't come. So C alone cannot be a key. So the only keys seems to be A, B, B, C, and B, D. Okay. Hence, this relationship having this, the closure of attributes is very, very important. Why we compute the closure. Okay. Now, all the dependencies, functional dependencies, can be inferred by this closure. For example, AB determines no, BC, all this set here. So given that there is a functional dependency, you can now use these sets to derive all the stuff that will hold on, the functional dependencies that will hold on. Okay, I'll again show you, maybe in a little deeper way. I'll show you in a nice graphical way how this can be understood. I'm going to put it for you a little later. Okay, right. But then, if I start going deep on this, this itself is a nice, no, one can understand this at a different level altogether. Okay, but then let's see. Okay, the idea is given a relation R and a set of functional dependencies, at least the set of attributes that completely determine, not its subset. Now you can see any of the subsets of this will not be able to determine, functionally determine all the attributes, and hence the subsets are not the keys. Okay, these are the keys. Now you can see BC and F, not in BC and F, since C and D are not super keys. C and D in this relationship are not super keys. So given this, one of the things that we want you to understand is, given a relation and a set of functional dependencies, how do you compute the keys? Okay, and how do you determine whether the relationship is in BC and F or not? This is what I want you to understand. When you're doing this exercise, one of the problems is going to be, we give a relation and a set of FDs, and we would like you to find out all the keys for the relationship, super keys for the relationship, and then determine which are all the FDs that violate the BCNF requirement. Okay, as far as the relationship is concerned. I'm going to give you a tutorial sheet consisting of a set of problems on which you can apply. You can do this yourself, and then I'll also supply the answers for those things, so that you can check and verify your understanding of it. Okay, this is very important concept, and you should suddenly learn this completely, so that it stays with you, as you go forward. Okay, right? Yeah. So I think that's the closure of attributes. I think I'm in this dependency preservation at 3NF. Okay. Now take this interesting relationship. Okay. I'm going to go a little deeper on a different this thing. Okay. And this is where I was talking about FD's closure and all that stuff. Okay. Now look at this relationship R. Okay. Right. Now this relationship is having A, B, C with the following FDs. A, B determines the C, C determines A. Okay, this is the. Now what are the keys for this relationship? A, B is the key to this relationship. Okay, because using A, B you can get all the other full set of attributes that are part of this relationship. This is not in BCNF because the C is not a super key. This side, when C determines A, this is not part of the super key. Okay. Now, since this is not in BCNF, if you split this relationship into AB and AC, Anbu, can you get me water? Okay. And also a tea. Yeah. Okay. Yeah. So you split this relationship into A and B and A and C. Now you can see the original FD, which is there on the relation ABC. Okay, AB determines the C. This is the original dependency. Okay, original FD. Now this cannot be applied either on R1 and R2. Okay, R1 doesn't have the C attribute. R2 doesn't have the B attribute. So in these two tables separately, in these two relations, R1 AB and R2 AC, you won't be able to preserve this dependency that A, B together determines the C. Okay, so you have brought this into BCNF, but it is not the same original relationship in terms of this dependency preservation. The only way you can preserve this dependency is by joining this relation, both relations, and checking, okay, whether this dependency is preserved. A, B together are preserving the, right? So dependency cannot be preserved by the split. Okay. So now one option for you is, I don't want duplication of data because of this FD, C to A. Okay. C to A will suddenly cause duplication of data. Okay. Because the C is not super key, C will get repeated. Since C gets repeated, because a C value determines the A value, there is going to be duplication because of this FD. To eliminate this duplication, if you split this relationship to bring it into BCNF so that there is no duplication of data, you get into this additional problem of dependency preservation being lost in the split. Okay, right? So this is the catch-22 situation. Okay, I want to avoid complete duplication, but in the process, the only alternative I have, there are 3 attributes and these are the dependencies. There is no way I can now have the no duplication of data and also dependency preservation of data at all. Then the only option is to get it into BCNF. BCNF will require that I split this original relation. Okay, F comes into picture. What 3NF will say is, look, this is a case where you should not get into BCNF. You should be happy with ensure dependency preservation, but causes some duplication of data. I don't really want to eliminate complete duplication of data if it is going to cause loss of the dependency preservation. So what is the option that 3NF requirement of BCNF, that every LHS of the functional dependency has to be a super key. What it says is, it's okay if the RHS of the functional dependency is part of some key requirements, the either or, okay. Now either this has to be true for a functional dependency or this has to be true. Now look at this previous case. This is the one which is violating the BCNF requirement. Okay, that C is not a super key. Now in this case, 3NF will say, third normal form will say, this is fine as long as A is part of a key. AB is a key. Now we say we are done. Okay, we don't further want to do anything, and then 3NF is a third normal form, which is a lower normal form than BCNF, in the sense that 3NF still suffers from some duplication of data, whereas in BCNF, going to be any duplication of data because every functional dependency key, the left side of every functional dependency is a super key. Whereas in the case of 3NF, the right side of it, if it is part of some key, you're going to relax this condition and you say, okay, let it suffer from some amount of duplication. But since I know it is going to be part of key, I will not worry about it. I will let this happen. Okay. Is why 3NF gives this relaxation is any split, because this is being part of the key. If you split it, you get into a problem. Okay, this is part of a key. This dependency is part of a key, and if you split it, the total key which is divided, okay. If you split now the relationship, it is difficult to do the dependency preservation. That way 3NF will provide you with this relaxation saying that, look, the right hand side is part of a key, don't bother now, okay, leave it at as you know, as a normal form at that point. Okay, so there is going to be some duplication of data, but it is probably unavoidable. That's what is going to give you this consideration here. Okay, right now I think that's what no. Now, as we gave here, 3NF is in 3NF. The original relation, which is not in BCNF, is in 3NF because A is part of the key here. Okay, right? I think last time we were also looking at an example. Okay, when to stop with 3NF. For example, take this example of a ration card example. Okay, you have a ration card number, name, and PAN card number. Okay, right? And I'm assuming this is not probably in reality true, but then I'm assuming that to just give you an example, I'm assuming this. Okay. Okay. I'm assuming that a person can have multiple ration cards. Okay. For example, you can have a ration card, separate ration card for kerosene, separate ration card for sugar. So it's not the same ration card people can use, but a ration card with a different number will be given for each one of these. Okay, I'm assuming that. Okay, I'm not sure in reality, the numbers are uniquely given for each one of the things they can obtain or take it. Okay, but let us assume that that's our case. Okay, multiple people can be associated with a ration card. For example, the whole family set of family names can be associated with this card number. Okay, all the family members can be associated under the same card number, which means that given a ration card, they're going to be not just one name, a set of names that will be part of this ration card. Okay, but every person will have a separate PAN card number. Okay, for example, so that's the reason why. No, little extra because I think I started late the class. Okay, I hope that is all right. Can I go a little extra time? Okay, okay. Sure, okay. So I started a little late. I think I lost the time because of the ABU thing in the beginning. Okay, yeah. So as you can see here, the ration card number and name are going to be unique. Since the ration card will get repeated for multiple names, okay, ration card number and the name will uniquely identify this record. So the key is ration card number and the name will be the key to this relationship. Okay. Now you can see this together determines the PAN card number because ration card number and name will be associated with the PAN card. Additionally, if the same person is appearing in the, for kerosene, for sugar, the same person name appears, his PAN card number has to be the same because given a person, his PAN card number is unique again. Okay, so PAN card number determines the name. Okay, this is exactly the same case where we had the previous. If you take this relation R, look at this relation R. This is exactly the example that I have actually dealing with in the previous case. Okay. Now, what are the functional dependencies? A and B together will determine the C. So, ration card number plus name will determine the PAN card number. Now, PAN card number will determine the name because once you have a PAN card number, that will determine the name of the person. Okay. Now, this is exactly the same case. Okay, sorry, this is A, right? Sorry, this is B. There, that is A. It doesn't matter. This in this particular case, it is B. Okay. C is determining the B value. Okay, that's instead of A, we have got B here. Okay, but now this is in 3NF. As you can see, this is in 3NF because name is part of the key. Okay, this is one which is violating the BCNF requirement, that is the super key, but name is now in a no, in the part of the key. Okay. Now, any split here, this relation will suffer from duplicate information due to PAN card number and name. That will get repeated. Okay, right? But preserve the dependency that given a ration card and a name, it will the PAN card can be checked now. PAN card, these two together will determine the PAN card number. This dependency will be preserved. Okay. Right. Let me just take one slide here and just explain this. Since because you need this dependency, you are not going to go into BCNF. If you go to BCNF and split this relationship into ration card name and the ration card and PAN card number, is a requirement that PAN card ration card number plus name should determine the PAN card number. Okay, that will be lost. You won't be able to make that dependency, preserve that dependency. Okay, I'll just take one new slide here. As you can see, I'm on the fly making these slides because I'm not using the board. I've got to the slides for the simple reason of the board was not working well for me. Okay, right? In the AView. Okay. Now this example, I'll just create some tuples and just show you what we are talking about. For example, let us say the ration card number is 101. Okay, this is the kerosene ration card number. Okay, the name is some Shanta or something like that. Okay, and their PAN card number is, let us say, 542 or something like that. Okay, right? Now, if you look at this, these two together will be unique. Given a ration card, for example, she can have a ration card. Let us say this is a kerosene ration card for Shanta. Okay, kerosene card for Shanta. Okay. Now, if she gets for sugar, now you can see Shanta. Okay, but then Shanta's this thing should be the same. 542 should be the same. So this gets repeated. Shanta 542 will get repeated because of that functional dependency. Okay, this is sugar card for Shanta. Okay. Okay. Now let us say there is also one Ramya in that house. So 101, Ramya will get one thing, but her PAN card is going to be different. Let us say it is 543 or something. 543. No, it cannot be just 542 because it is already given to. So this is a kerosene. Okay. Kerosene card for Ramya. Okay. Right. So now you can see similarly 102 also will be there here. Okay. Now this will be Ramya. Now 543 will again will repeat it. Okay. Okay. Only thing is what will not get repeated is the card number plus the name. You don't find multiple. So this becomes the key. Okay. For this entire thing. Okay. But then this relation, because you want to preserve this dependency, given a card number, ration card number and a name, the PAN number is going to be unique. This determines the, again this is sugar card for Ramya. Okay. Okay. This example should make it clear. This is in 3NF. Okay. Because of this dependency here, the dependency is PAN card to name. Okay, this will get repeated. 542 is Shanta. 542 is Shanta. This will get repeated. There's no way to actually avoid this redundancy. Now, Shanta's PAN card number changes. You will have all those problems going there and changing it everywhere. Okay, but then you don't want to further split this into PAN card name one relation, PAN card and ration card number into another relation, because that will not preserve the dependency that given a ration card number, given a name, that will determine the PAN card number. Okay, that will not be able to be enforced if you split this into the so you will stop at 3NF because of that reason. Okay, right? When to stop with 3NF is this. Okay. with this example, it should be clear, okay, when we want to stop with 3NF, okay. When we can't actually, by splitting, we can't preserve the original dependencies which are there in the relationship, you are not going to go further down and then split that into BCNF, okay. To achieve BCNF, you are not going to sacrifice on the dependencies, okay. I hope with that it's clear, okay. I'll also trivially do the 2NF and then 1NF and then stop there. This is for completeness sake. Nobody will actually stop with 2NF because 2NF will cause a lot more duplication, okay, right? And 1NF is just every relation is going to be in 1NF, but then 1NF will cause all the problems that we're talking about. Unless you get to BCNF, complete duplication of data cannot be avoided because of FDs. Okay, so all the other lower normal forms will cause duplication of data. Okay, because of FDs, because of functional dependencies, every other normal form will cause duplication of data. Okay, so for completeness sake, I am also doing the 2NF. Okay, what is second normal form? Given a relation R, A1, A1, A2, A3 attributes, okay, if A1 and A2 is the key and A3 is non-prime attribute, all that 2NF, second normal form, says is it prevents non-prime attributes to be partially dependent on the key attributes. Okay, relation is in 2NF if there is no partial dependency of the prime attributes on the key attributes. For example, you can see here, if A3, which is a non-prime attribute, this is not part of the key, okay? If the non-prime attributes are partially dependent on the key attributes, here it's only dependent on A1, not on A1 and A2, then it would have become a full dependency on the key. It is dependent on only part of the key, okay? If there is an FD such as A1 now determines AC, A3, the relation is not in 2NF since non-prime attribute A3 is dependent on only A1, which is part of the key. Okay, 2NF says that all non-prime attributes should be dependent on the fully on the key attributes. That's the only requirement for something to be in okay. But it doesn't prevent duplication if there are FDs between the non-prime attributes. Okay, it is not talking about non-key attributes, non-prime attributes. Okay, if there are dependencies, 2NF will not talk about it. A 2NF will only require that all the non-prime attributes should be fully functionally dependent on the prime attributes. Okay. Then it is actually called it is in 2NF. Okay, does not prevent duplication of data if other FDs are present among non-prime attributes as well. Okay. Then for completeness sake, we will also look at the first normal form. Okay, what is first normal form? All attributes in a relation are atomic. This is as an including part of the definition of relational model itself. Okay, for example, a student record, if you take the student name and address, if the student name has subparts like surname, middle name, given name, it has actually 3 sub attributes. It's not one single atomic attribute, but then it has subfields. Okay, for example, if you're talking about a table, a column, now a column is split into subcolumns. Okay, student name column is split into surname, middle name, and given name. Then student name is not atomic. Okay, it has only one value. Okay, it is 3 subparts to this attribute now. Similarly, the address attribute has street, door number, etc. Then the relation is not in 1NF. Okay, first normal form. First normal form requires that every attribute is atomic. It cannot be further split. Okay, that's the requirement of first normal form. Okay, so we will repeat this. First normal form is very trivial and simple. All attributes in the relationship are atomic. Second normal form requires that all non-prime attributes are fully dependent on the keys. Okay, they're not partially dependent on the keys. Third normal form requires that okay, either for every FD in the relationship, either LHS is the super key or RHS is part of some key, then the relation is in third normal form. Then BCNF requires that, okay, this is what we saw, okay. BCNF requires that every functional dependency is reflected as a key constraint. The left-hand side of the functional dependency is a super key for the relationship, okay, right? We would like to achieve BCNF because BCNF avoids all kinds of duplication as far as relation is concerned where functional dependencies are involved, okay, right? I think yeah, I've sort of, when functional dependencies are involved, I actually gave you some understanding of the normal forms, okay? I'm going to go further deep. This normal forms is still not, no, I've done intuitive understanding for you for the normal forms. What I'll do is, I'll just do this thing to see, okay? This is a final example, but then after this, I'm going to go into, how we are going to, split the relationships. I'm going to look at formal ways in which we're going to do the dependency preservation, what is a lossless join, and then I'm going to do the multi-valued dependency and also the join dependency, which will result in fourth normal form and the fifth normal form, okay, right? So we have still some deeper stuff still left in this particular thing. So I will just revisit this property record and see which normal form it is in, okay. Now look at this property record. We have the property number. This is where I will stop, okay. I'm reaching 3:45. The next 5 minutes I will close, okay. I probably have taken some 20 minutes extra today, but then I started late because of the AV, okay. The property number, city, house number, area, price, and tax. This is what the property record we took. The candidate keys for this record are property number and city and house number, okay. The FDs also we saw previously, okay. What is this relationship in, no, which normal form this relationship is in, okay, right? It's suddenly not in BCNF, that we have already seen, okay. Is it in third normal form, okay? I'm not going to answer this question. Is this in second normal form? I'm not going to answer that question. Is this in first normal form? I'll answer that question, okay? The answer for that question is property number is atomic, city is atomic, house number is atomic, area is atomic, price is atomic, values, okay? Tax is atomic attribute. So this is suddenly in first normal form, okay? Every relation normal in relational model can be assumed to be in first normal form because we don't permit attributes to be further split, okay? We are not assuming a second order relational model where an attribute itself can be a relation again, okay? We're not ensuring that. So as part of the relational model, it's in first normal form. We also saw that this is not in BCNF, that we have already shown, because both these violate the requirements of BCNF. Area is not a key, city is not a key. So we know it's not in BCNF. I leave it as an exercise for you to figure out whether it is in third normal form or second normal form. That I'm not going to answer this, but will expect you to actually work it out yourself and see. I'm going to do more examples to see whether you can identify which normal form a relation is in, okay, by doing more exercises and more tutorial problems as we go further, okay.